In this section, we're looking at logarithmic functions. Remember, exponential functions and logarithms are inverses of each other, and we need to be able to write back and forth between the two. So for example, if I have this exponential function where we have our variable is an exponent, to be able to solve this, I need to rewrite it as a logarithm. So my base is the base. So here I have base 7, so I'm going to go log base 7 of 343 is equal to x. And so this part we can plug into our calculator and we can figure out 7 raised to what power is equal to 343. So if I have log, now remember in your calculator, some of yours will be able to put in a base 7, some will not. This is where we would have to use our change of base formula. I'll have to rewrite that as the log of 343 over the log of 7, because your calculators are set up where your base is 10. And so when I plug this in, this is considering a base 10. If I plug in 343 divided by log of 7, then it treats it as if this is what we're writing here, log base 7 of 343, and it'll tell me that my x value is 3, which means 7 raised to the third power is equal to 343. Now, the other part of this that we need to be able to do is, what if I'm given if we're given that we have our variable within the logarithm, so now I'm looking at log base 5 of y equals 4. We need to be able to rewrite this as an exponential function, and so we would have 5 raised to the 4th power is equal to y. And again, we can now use our calculator at this position, so we have 5 raised to the 4th is 625. So our y value is 625, which means that the log base 5 of 625 is equal to 4. So we need to be able to go back and forth between the two. We had the example where we were going to invest the $400 at 6% for 3 years, and it was going to be compounded continuously, and we solved that problem. What if we're looking at how long it takes to double the money? In this same sort of scenario, we're going to compound it continuously, so we're still using the same formula, but now we're looking how long does it take to double the money. So doubling the 400 would be $800. We know we started off with 400. We're raising this because of the continuously being compounded. This is our e raised to the r times t. Remember, our rate is 6%. Now we're looking for our t, that's our time. Now we know that e goes with continuous change. Here, as far as solving that, this is where we're going to be using the natural log. First, I'm going to divide both sides by 400. We know we're doubling our money, so that's why we're looking at the 2 there. We have our e raised to the 0.06 times t. And if I take the natural log of both sides, what that looks like is the natural log of 2 would then be equal to natural log of e. Those are inverses, they cancel each other out. So we're looking at the 0.06 times t. So now we can solve for t. We do need to use our calculator to do the natural log of 2. We can see that that is equal to this 0.6931 value. I do still need to divide both sides by this 0.06 to solve for t. So if I take the natural log of 2 that I've already done and I divide that by our rate of 0.06, we can see that it's going to take 11.55. So that's our t value, is 11.55 years. So with our continuously compounded interest, it would take 11.55 years to double our money. Looking at the graphs of logarithms, if we start off looking at what we had before with exponential growth, the inverse, we're still talking base 2 of x, we're just flip-flopping our x and our y's. And so where we had a y-intercept here at 0, 1, we'll now have an x-intercept at 1, 0. And where we had our horizontal asymptote where y was equal to 0, we will now have a vertical asymptote where x is equal to 0. So for this particular graph, where we have a base of 2, now it's going to be going through, here we were at 1, 2, now we're going to be at 2, 1, and then this point at 4, 2, so I'm over 4 and I'm up 2, and we can see now that as this piece goes down here, it's going to approach but never touch that line, and then goes up this direction. And remember, we're saying that these are inverses of each other, so they would be symmetric to the line y equals x. Same idea then with our decay problem. Now we again have our horizontal asymptote for our original function that was our exponential decay. So now that would be a vertical asymptote where x equals 0. Again, we were going through this point at 0, 1, and so now it's going to be at 1, 0, and then we were at, if I'm was at negative 1, 2, now we're at 2, negative 1, so I'm going over 2 and then down 1. And here we're at 4, negative 2, so it's going to go over 4, down 2. And so where we're coming in this direction now, it's going to go up the y-axis and comes off this direction again, symmetrical to that line y equals x. Looking at a logarithmic function like this, where we have log of base 5 of x minus 1 plus 4, this, to begin with, the x minus 1 tells us that we're going to shift right 1. So one thing we'll have to pay attention to with that as far as shifting left and right is that's going to change where our vertical asymptote is going to be. It also, we have the plus 4, so it's going to move this up 4. So one thing that we could do as far as helping ourselves graph this is come up with some points. Now if you want to do it out of this, where we're plugging points in and trying to figure it out that way, we can. Or we could, if we change this into an exponential function, sometimes that's easier to work with as far as our table goes. So I'm going to show how we can do that. We're going to change this to exponential, and then we're going to make that's going to be step number 1. Step 2, we're going to make a table. And then we're going to, because we're actually graphing the logarithm, we're going to flip our x and y to get back to our original. So for example, we're going to rewrite this. We know we have 5. It's going to be, we'll say 5 to the x, I'm switching this, 5 to the x is equal to y minus 1 plus 4. So that goes to plus 3, and I'm going to move that over to this other side. So we have 5 to the x minus 3 is equal to our y value. So this would be our inverse. So then as far as making that table, I'm going to pick some points to plug in there. So if I have 5 to the 0 power, that's equal to 1. 1 minus 3 is negative 2. If I plug in 1, 5 to the first power is 5. Minus 3 is 2. If I plug in 2, that's going to be 5 squared is 25. 25 minus 3 is 22. So we can get some points that way. That also then gives us that if we're looking at our original equation, because this was for our inverse, if we're looking at that original equation, we're going to flip-flop those so we have ordered pairs at negative 2, 1, and at 2, 1, and at 22, 2. And then we can plot those points for our graph.